This is not clear enough.
Finish him. Kill the guy now. Grab the gun. Beat him.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We £5 on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Arise and shine.
Okay, you're welcome to this second lecture we are having today. In the last class, that's in the lecture 1 of the series, we have studied some concepts on accumulation points. We've reviewed topology. We've looked at types of topology. We've looked at some other things, isolated points, and so on. We've seen when a set is said to be closed and how to obtain the derived set and all the rest. So today we continue with some of these basic concepts in topology. So we want to take a look at some definitions. Number 1, here you have, we want to look at what we call a closure point. A closure point okay, you say point P, a point P is, this P belongs to A, and A, of course, is a subset of X, is said to be a closure point if P belongs to the closure of A and P belongs to the derived sets of A. So you see there, we've already defined what you mean by a derived set yesterday, and we have said that it's a set of limit points. And today, if you have a point belonging to the derived set, and that point is also in the closure of a set A, say A, then that point is a closure point. Then we need to also understand what we mean by what we call dense, a set that is dense, the denseness of a set. Okay? So we note that too. A set A, which is subset of a topological space X, is dense in X if the closure of A is a subset of X. Okay? Then it is the set too can be said to be a set that is a subset of X is everywhere dense. Everywhere dense. Dense in X if the closure of A is equals to X. So we note this. 3. We also say the set A, which is a subset of X is nowhere dense. This one is everywhere dense. This one nowhere dense in X. If the closure of the exterior of A, if the closure of the exterior of A is equals to X, is equals to X. Of course, we know what the exterior of X is. Last class, we said the exterior of X, of A here is equals to the interior of the complement of A. Okay? So when you say that you are looking at the closure of that, that means you are taking the closure of this. And we say that this is nowhere dense in A if this is equals to X. Some books look at it as when the interior, the closure of the interior of A is equals to empty set. So whichever of these two you use, you are saying the same thing. So if you are looking at the interior of A and you take the closure of A, and what you get there is what? Is an empty set. Then it's nowhere dense. You cannot find anything both inside A nor its closure. So it's nowhere dense. So that is for that. So let's look at at least one example of a situation such as this. Let me take a question from my little text here. An example. Okay? Consider X to be equals to A, B, C, D, E. Okay? With closed sets. Okay? We want to give the closed sets in this set. So, and we give them those. The closed sets here include empty sets. We can also take X to be a closed set of this. And then we take B, C, D, E. Okay? This closed set can actually be obtained from a topology. If you are given a topology on X, you can define the closed set. Likewise, if you are given the closed set of X, you can also obtain the topology of X. Now, let's take a look at this. We have A, B, E, and then we have B, E, and then we have singleton A. So if these are the closed sets of a defined on X, we can define the topology from this. Okay? So let me just give you a chip in on how to obtain the topology from this. Now, the topology on X will be made up of open sets. And to obtain the open sets here, what you simply need to do is to take the complement of empty set with relative to X. So X take away the empty set, first of all, will give us X. X take away itself will give us an empty set. X take away the set B, C, D, E. We'll be left with only this singleton set. Okay? And then X take away ABE. What would that give you? That should give you CD. And then X take away BE, which is a closed set. What would that give you? You'll be left with ACD. And then X take away singleton A will give you B, C, D, E. So, of course, so from the closed set listed here, you can define the topology on X. Now, if you can, from the closed set you are given, obtain the open set which forms the topology on X. Now, the next thing we want to do, what if you are given a set and you are told to obtain the closure of that set in this case? Let me look at for instance, you want to obtain the closure, obtain the closure A, C. You want to obtain the closure of this set. The closure of this set is simply the intersection of all closed sets, let me call them closed subsets of X, okay? Such that the closed subset of X here contains this set made up of pair of points, A and C. And so where C is regarded as X take away any open set. So let's ask ourselves, of all the closed sets listed here, which one contains AC? Of course, X is one of them. X is a closed set there. It's one of the sets. Of course, you see X is A, B, C, D, E, and it contains AC. So, X is one of the closed sets. We take other intersection. Which of these other sets is made up of any set that contains AC? This does not contain AC. This does not contain AC. A does not contain AC. Neither does empty set contain AC. So, of course, X is undisputably the closure of AC. And what do we say about this set? Based on the definition of denseness of a set, we see that the closure of AC is what? In X. Of course, we know AC is a subset of X. But the closure of AC here is equal to X. Therefore, we say that AC is everywhere dense in X. Very simple. Very simple. So we see there the possibility of having denseness. Now we want to take a look at some short propositions which will be proved, and then at least you will see how we dwell on this. This is just an example, but how do we dwell on it using the definitions we've already given? So let's take a look at some propositions and draw out an argument that a logical argument that will prove those propositions. Okay? And mind you, some of these propositions can formulate questions that students can be asked. Now, we want you to look at this claim. The closure of an empty set is an empty set. 2. We'll also look at the closure of a union. Can we say that this is equal to the closure, the union of two closed sets? We look at number 3, the closure of closure is equals to the closure of a set. And number 4, we want to take derived sets. Derived sets. Can we say, okay, the union of two derived sets will give us the derived set of the union of two sets? Can we make these claims? So let us prove these propositions. How do we bring about the proof of this proposition? Now, of course, you know, already said, an empty set is both closed and open. So the argument of number 1 is very trivial. An empty set is a clopun set. It is both closed as well as what? Open. Therefore, you can simply draw the conclusion straight away that the closure of an empty set is itself. You need no further argument. Now, let's look at the closure of a union of sets. By definition, the closure of A union B must be the intersection of all closed sets contained in X such that the closed sets contain A union B, where C is X take away U. Of course, you know that here U is a member of the topology on X, an open set. Now, what happens? Can we simplify this? Of course, you know that if C contains A union B, it means that C must contain A, it must or contain B, and it can also contain both of them. This is what I mean. Now, this means you take intersection over C in X, and you see that C here contains A. Okay? Contains A. And we also notice here that because this claim is or, so when you have or, you have the union. So you have, this is an intersection of C contained in X, of C containing B. All right? Okay? And then, or the intersection over C again, containing X, where C contains A intersects B. Good. So, don't be confused. This is C, a subset of X. So you can see clearly, by definition, you say A, X belongs to A union B if X belongs to A, or X belongs to B, or X belongs to A intersects B. So this word or is represented by the union. So in other words, we say here that you can break this down into all closed sets containing A, union all closed sets containing B, union all closed sets containing A intersects B. So, now this here can be, it may not always be true. If A intersects B, for instance, a disjoint set, that is, if A intersects B is an empty set. So, what do we do with this? We can now claim that this is a subset of what? This union this. We can exclude this. And if we exclude this, that means what we are going to have is the closure of A union the closure of B. Now, so this is not absolutely true, so we can make a claim here that this is actually contained in this. Why this contained? Why is it not equal? Because of this intersection that we have here. So that is the second claim. So this should be the correct thing there. Now we look at number 3. Let's see how we prove that. The closure of closure. This simply means intersection by definition. This number 3. Okay. By definition, this means the closure over, the intersection over all a closed subset of X, such that the closed subset of X here contains A bar, which is the closure of A closed, okay, where C is equals to X take away the open set. All right. By definition. Now, if this is the case, and you have this as the closure of A, now, I'm going to give this closed set here. Let me give it a number. let me call it 2. Okay? Let me call it 2. Okay? Now you can always, and you can, there's also a possibility of having another closed set that is smaller than C2, and so that we have C2 containing C1. Okay? So that you have C1 containing A, such that C1, perhaps let me call this one too, U2. C1 is X take away U1. And U1 belongs there. So we see here that you can always have a closed set that is larger than another closed set. But this closed set contains A itself. So with what we have here, you will look for the smallest, because here we are looking at intersection. What intersection does is that it restricts. Intersection restricts the set. So this here will give us simply the closure over the intersection over a closed set, C1 in X, so that C1 contains A and C1 is same as defined up here. Hence, what we have here is the closure of A. Now, that takes care of that. So the closure of A is, now let's look at it this way. You have the incidents, okay, where you have border closure in practical sense. Suppose you have a border closure in your country, and then you also have another border, another closure before the closure of the main border. Anybody that wants to get out of your country cannot leave the internal border, not to talk of getting to the outside border. So once the border inside is closed, that country has what we call a border closure. Nobody can leave that country, be it interior or exterior. So that is what we mean here, that the closure of a set A is equal to the closure of A. So if you like, place as many ladders of closure on a set, it will always lead to the closure of the set. For instance, another thing we could say is that you see a particular snake dead on the floor, and you say this snake must still die. And you take your machete or your knife and you cut it in bits, it will still remain dead. How many ways can somebody physically at this time die? He can only die once. So even if he has died and then you take him again, you put him before the firing squad and you keep on firing as many bullets He will not, you may say he will die 1,000 times, but the truth is that he has died. Do you get what I'm trying to say? So that is an implication of that in a practical sense. Now, we want to look at the union of derived sets. The union of derived sets. That is number 4. We want to see the proof of that. Now, you agree with me that when we talk about A prime, you've been told that this is simply a set containing limit points, such that this is A intersect U, take away singleton P, where U is an open set. In same vein, you may decide to also define B prime in a similar way. And so we say, okay, let this be P such that you have B intersect U without P, where U, okay, we may choose a different open set here and claim that that open set is V. Okay. And you need to take the union of this. Taking the union of this will simply imply, of course, sorry, this is not equal to empty set by definition. Let me put this right. It's not empty, where U belongs to tau of X. And this also is not empty, where this belongs to tau of X. So, if you want to take the union of this, it's very clear. The union of A union B, A prime union B prime will yield let me make this clear. It's not compulsory that the points here must be the same. You can have a different cluster point here, a different set of cluster points. It doesn't make any difference. And so, whichever way you want to take the union of this, it will be a set of points. Maybe 1, or it may be 2. Because we are talking about union here. When you take union, it may be any of the 2. Okay? And so what are we going to have here? We have A union B, okay, intersect. What do you have here? U union V, okay? And I want you to know that the union of two open sets is open. So, and then this can take away P1, P2, because both of them, in this case, are accumulation points. So, the truth is that the intersection between these two will not be empty. it wouldn't be empty. And thus, it will now claim that the new accumulation point is P prime, such that, what do you have here? A union B intersect. The union of two open sets is itself what? Open. That means U union V, if I say let this be W, will still be in the topology because of the axiom of arbitrary union of open sets. By the axiom of arbitrary union of open sets, the union of two open sets is open because it is expected that the topology must still contain the union of any number of open sets inside it. So, by this now, this can become this, and then we can now have that not equal to empty set. And what we have is as simple as the derived set of A union B. So you have exercises you can make do with in the material. So we are done with the concept of accumulation point, closure of sets, derived sets, and we've seen how to prove any proposition that we are given in these regards. Another thing we need to know, you know, a set has some characteristics. You can view a set based on its size. You can also view it based on what it contains. Now, we recollect that the building block of a topology is sets themselves. And so these two sets may not have the same cardinality. They may have different cardinality. As we can have two sets comparable, you can compare a set X and Y. You may decide to say, okay, X is subset of Y. Don't forget, if X is subset of Y, that means that the power set of X will also be the subset of the power set of Y. You can compare two sets. You can as well compare the power sets. Okay? Let's assume that the cardinality of X is 3 and the cardinality of Y is 4. What are we saying? If you want to find the cardinality of this, that will be 2 raised to power the cardinality of X, which gives you what? 2 raised to power 3, and that is what? And the cardinality of Y here is 4, and that gives you what? 16. Of course, you see that 8 is less than 16. So if you can compare two sets, you can also compare the power set. Now, another thing we need to know is that if the topology on X is a subset of the power set, then it means that you can also compare the topology in Y. So you can compare. So if you can say, okay, this one is a class of sets that are subset of the power set, you can always obtain two topologies that are comparable. And the source of comparison is the subset operator. Now, when you have two topologies that are comparable, the larger one is called the strong topology, or let me not put it that way. Let me call it the fine topology. The fine topology or the larger topology. Now, then the smaller one is called the coarse topology. So, in this case here, the smaller topology is called the coarse topology, the coarse or the weak topology, and the larger one is called the what? The fine topology, as well as the large topology. The fine topology as well as the large topology. So you can compare two topologies, and that is what leads us to the weak as well as the fine topology. Now, having that at the back of our minds, we can have two topologies. One is weak, one is strong, or one is large. This is weak, this is strong, this is large, this is coarse, this is fine, this is weak. You can use them interchangeably. So it could be observed that on a single set, you can obtain as many topologies as possible on a set X. And when you have many topology, we can have a family of topologies. Okay? A family of topologies. So, as many of these topologies that you can have, and these topologies can be compared. They are comparable. So you can say, okay, topology K, okay, precedes topology L, okay, for some K, L inside J. So you can have comparison of two topologies. If this precedes this, this is smaller than this. So it's just another way of putting it in this form. So with that, we are done with lecture 2. I believe if you have questions in this direction, you can contact me through my WhatsApp group. Thank you.
Grab the gun. Beat him. What's wrong with you?
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We by pounds on you. Very stupid. We are changing that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Arise,